Okay, can everyone hear me? Just good. Yeah. Right. So, and then I imagine you guys can see the screen share here where it says no structures, which is what we're going to be covering today. So the plan, of course, for the rest of the course is that I'll just give this lecture today. Then we're not going to have lecture this Friday, but I might contact people about their project status. And then we're going to have the final recitation next Tuesday. I have to give you guys a week to work on that. So I'll release this the recitation, which is based on the lecture today. All right. Okay. So are there any questions before I start on the lecture? Okay. I'll just keep an eye on the chat here if there's any questions. All right. So what we're covering today is no structures. So basically, let's see here. How do we manage data that has no or very little immediate structure? So this is kind of it's a kind of a tough area, but it's an area that gets confronted quite a bit. So the motivation is this: is that most of the data that's out there, I mean, if you really think about it, most of the data out there is has no structure or is very semi-structured. Okay, so things like text files, emails, HTMLs, PDFs, etc. So this stuff is I mean, some at one point someone came up with some statistics about. It's very hard to measure, but I mean, over 90% of the data, the quote data out there, is of this kind of form. So it's just, I mean, there's other kind of forms that you can maybe say are no structures, but these are the kind of the primary ones. I mean, the things like sensor data, which is kind of structured in some sense, it's very simple structure, just like a time series of measurements. But so somebody might, I mean, it's very hard to argue with this because you might say, well, like all the data that NASA is taking, and I mean, which is just sensor data, that's actually eclipsing what all the written text is. But so I don't know how to measure how much information out there. But certainly in the day-to-day, in day-to-day dealings with data, we come across quite a bit of this unstructured or what I would call zero structure or semi-structured data. So we want to use this for some purpose. I mean, there's a lot of valuable data. I mean, there's a lot of applications where you think, well, you might want to use this. So for instance, we might want to say something like, well, we have all these product reviews from these different restaurants. People are just typing in their or tweeting about stuff. They're just typing this stuff in, and we'd like to kind of glean some kind of useful information from that. Like, is this a good restaurant? Okay, so that might, I mean, if everybody says that the food tastes like garbage, then that's probably not a good sign that it's a good restaurant. So that would be information that we would there's information that we'd like to get put to use. All right, so there's kind of a fundamental choice here that one is presented with, and the first choice is kind of what a lot of researchers and a lot of visionaries have adopted, and then the second choice is kind of a bit more practical and maybe is what really gets used, but we'll see. So the fundamental choice is between something that's called essentially the semantic web, which I think some people have heard of. Has anybody heard of semantic web before? You ever hear of that term being used? And so the idea here basically is that treat the entire web as a database. So there's all that data out there. So leave it in place and then build engines that can search and extract information from that, so that you just look at the whole web as just a giant source of information that you can then query. Right? So in some sense, as we'll come to later a little bit, I mean, this is kind of this started out was kind of, I mean, in some sense we have this, but the semantic web vision is a lot more ambitious than actually what we have at the current time. We'll get to that in a second. But then the second choice, which I'm afraid is the one that really is kind of this is the one that is mostly adopted. I mean, it's basically that you just have a private database that you've designed for your own use, whatever it might be, whatever branch you're in. I mean, presumably you're out there doing work for a reason. But you, in this private database, solution, what you're going to, instead of being so ambitious as to kind of provide this kind of universal library and all this kind of stuff, what you do is instead is you basically just suck in and bring information in and curate it in your own kind of data store. Now, it might be that you share that data. You might build a website over that data that you then allow people to search. But the point is that you've curated, you've organized the data in a centralized database. All right, so let's talk about the semantic web. So the semantic web, like the additional ideas behind the semantic web were developed by this Tim Berners-Lee, and he's a big person because he was working at CERN back in the day when they came up with the HTTP and basically the web. So he's essentially what they call the father of the web. So so from that, he went on and he, I mean, if you think about like what was going on, I mean, I'm not sure if you guys have heard the idea that, well, the whole story that at CERN, they basically wanted to kind of have a way to share papers and data. And Berners-Lee was working there, and these are really, these are a bunch of physicists, so they've got a lot, they're pretty talented people and all that, and they have lots of ideas about how to do this stuff. But basically, HTTP comes along so that they can develop this, and then HTML comes along a little bit later. That's Mark Andreessen, and that's where they have the image tags like that. So and then the first browser, which was Mosaic. So this so it starts with that. But one of the ideas then was that they wanted to that with the semantic web, as it gets kind of elaborated, and here are two kind of architectural diagrams of the semantic web that we'll just discuss a little bit here. But the idea basically is that you have this kind of core. So the initial web, like Web 1.0 or whatever it might be, had these kind of very, very core protocols like HTTP, HTML. So then the whole idea of a URL and a URI. So there's URIs, or there's the named and URLs. We'll get to that in a second. But there's kind of a set of foundational technologies, but then the idea that you're supposed to build up something that's kind of that is able to kind of provide semantics, so meaning to this data, so that basically as people will then rally around these standards and contribute data in according to these semantics, and basically do this according to kind of shared namespaces, and so there'll be some kind of reference kind of meaning over what these things are, and that you'll get this kind of organic buildup of data that can then be queried. Right. So that was kind of the whole idea behind the semantic web. And it's not just data; it's also like interoperation. So I mean, one of the classic examples was this kind of booking. I believe it was booking of a doctor's appointment, where they developed in the semantic web. They developed this kind of idea that you're interacting almost like a database, but you're interacting over all this kind of open data. So that was kind of what was driving it, or what is driving it. This is, if we look at these, we'll come back to these diagrams actually. And the fact is, I just pulled these two diagrams, but it's kind of, it's a little bit kind of troublesome in some sense that they're not really, I'm not really sure with the date on these different diagrams, or these architectural diagrams, but it's already kind of a little bit, it's becoming a little bit of an alphabet soup, which maybe is a criticism, which is a criticism. But it's the fact is that they're different. So there's lots of different. It's very much an evolving type of architectural revision. So that's been a little bit of its what caused a little bit of some of the problems. We'll talk about that in a second here. So first of all, I think some of you guys have seen this already, especially people who had the Database 1 course with me. So let's just talk about the web kind of stuff and these kind of things. Okay, so again, I mean, I could look it up. I have no idea what an IRI is. I don't know, but I know what a URI is. And I know what a URL is. So a URI is basically just a name out there, and a URL is a location. So URI provides a namespace for kind of a systematic way to name things, and so that you have a one-to-one correspondence between things and their names. This is something that because of because you define your own namespaces, I mean, you can keep these things distinct. So like, for instance, if you have something like IBM, if you just have that as a global name, that's not going to work, because people are going to have different, I mean, IBM is maybe not the best example, because IBM refers to the corporation, but if we have some things that we might have acronyms that have, we can't just use the acronym, for instance, BLG or something. So BLG might mean a lot of different things in a lot of different contexts. But if you preface that with a namespace, then you can get it so that the mapping from namespace colon BLG, then as long as that namespace is unambiguous, so you point to one particular namespace, then it's unambiguous, that reference. Okay, so that's the whole idea behind a URI. All right, so then we have a set of other kind of standards. We have Unicode, which is a great standard. So we have these kind of low-level standards, which are very strong and very useful. And then we have, so we're just building up here, we have XML. So if you recall in the Database 1 course, for those who took it with me, we did a lot with just kind of basic XML. I mean, it's got some benefits. So this was kind of one of the first things that was kind of a contribution of the semantic web, was this kind of notion that we're going to kind of do things around XML. And then if you recall also from the database course, then we also look at things like XML query or XQuery, and also XPath, but it's not mentioned here. So there's like, well, where's XPath? Okay, well, XPath is somewhere, but there's one of the criticisms with the W3C stuff is it's just a big alphabet soup. And there's all these different standards. They're really kind of standards happy. And the problem with that, of course, is it leads to, it's not like databases, it's kind of like, oh, you have SQL, but you can keep the discussion kind of focused. The problem is that it then becomes kind of, when you get to there's a lot of people just that rattle these things off, and it becomes kind of almost a prestige thing, how many acronyms you know. And that's really a bad sign. Typically that turns people off. People want to approach things in a very simple way. Like spreadsheets and databases are so simple that anybody can do it. And that's really, you don't have to have a lot of acronyms floating around. And that's one of the things that has been a problem with the semantic web. Anyways, we did cover this before, so I hope that for those who didn't take the Database 1 class with me, and it's XQuery and XPath are these query languages that work over XML. Okay, we have the notion of Unicode. Again, I said that before, that was fine. Then we have namespaces. So that's good. So that's helping us kind of resolve these URIs. Now we get up to something like XML schema, where you're putting types. So it's kind of enriching XML. So this is kind of getting a little bit heavier weight. All right, then we get up to something which I'll cover in a second here, which is called RDF. Has anybody heard of RDF before? Resource Description Framework? Okay, so this is kind of beginning where we're starting to form a data model by which we're going to organize all this data. All right, and now historically, that data model is actually that data model is what's called a if you go way back in the literature, it's basically a semantic network. All right, so it's this idea. I think I talked about it in the Database 1 course, where you're just kind of willy-nilly building up a graph. So this idea that, like, I think the example I used in the Database 1 course, as I said to you guys, I said, hey, everybody, could you just start writing this graph out where you mention yourself, and then you can pick whatever predicates you want to associate with yourself. You can say, like, okay, me, and I have a pet, and my pet's name is Spot, and then Spot is a dog. So one person is going off and they're kind of describing their pet. Another person is going off and describing their car. Another person is going off and like describing their family. They're doing links to other people. And then so basically everybody's just kind of building out these graphs in a willy-nilly way. And it's useful in the sense that it's like, you don't have to go and consult some database schema to do this. You can just kind of do it, which is a great virtue, actually, because you can kind of cluelessly just kind of build out information. But it leads to kind of control problems pretty quickly. But RDF, with all the, with all the talk, and it's essentially just that. That's all it is. It's just building out a graph. Okay. Now, once you get to RDF, so that's okay, I suppose. Now, the thing is that the original RDF was just a gigantic syntactic nightmare. I mean, the way you actually specify stuff, you had all this clutter. Now they've gotten it better, and they have this thing that's called turtle syntax, which I'll show you in a second. we're not even gonna touch the basic RDF, because basic RDF is just terrible in terms of it's unreadable. It's a mess. just syntactically the way you have to deal with it. So turtle is actually the way you do it. Anyways, okay, so they finally got to turtle. And then the thing is, now upon that, now what they did is they built up what are called ontologies using OWL. So, okay, so if we look over here, we see, all right, they have a query language that goes over RDF now called Sparkle. And then they have ontologies in OWL. And then they have these rules. So then all this stuff up here starts is much, much less used. So, because again, the learning curve to kind of get into this stuff and to start doing this stuff up here is very, very difficult. And I'll also just talk a little bit about some limitations of this OWL stuff. But I mean, I think the people in the semantic web community would not really like this for me to say it this way. But I would basically say OWL is kind of a glorified way to define views over RDF data. All right, so we'll show. Okay, so this is basic. Okay, so and then you get into stuff right here where you say trusted semantic web and proof and logic and okay, now you have crypto on the side. I mean, it's like it's a big thing that I don't know. I mean, what's trust? I mean, I don't know. I mean, okay, maybe because you do crypto and then you want to make sure. Anyways, it's big. All right, so let's just try to get our hands around a little piece of this thing, so that we can kind of at least it's just not, it doesn't become just gobbledygook. All right, so RDF is founded on the notion of these triples. So this kind of like as I was saying, you're building out this graph, this triples of subject, predicate, object. All right, that's kind of what these are. So that's actually kind of a data model. That's kind of a linguistic data model: subject, predicate, object. So basically, we might say something like this: Mike is CEO of C-Phrase Technologies, which is, that's the truth. And then we also might then just say C-Phrase Technologies serves Acme Corporation, right? So what we're doing here is we're specifying these triples. So all we need is just all we need is simply a relation of 3 attributes, or a table of 3 columns. To support this, and then we say maybe something like Mike's hire date was 2000, that particular date. Now the thing is that this is just kind of conceptually what RDF is doing, but then we got to make this thing kind of work with these namespaces and these URIs. So basically, the subjects and the predicates are all going to be URIs. All right, they're going to point to some kind of reference notion or a namespace and the value out on the web somewhere, so that we have an unambiguous, or at least we have a single meaning for these things. And then the objects are either literals or URIs. Okay, so the objects can also be a URI, or they can just be a literal value, like 20, or the string, C-Phrase Technologies, or the date, 2018-07. 14. All right, so like I said before, the actual RDF syntax, I'm not really sure how many people want to use that anymore, but basically what they have now is they have the turtle syntax. So the turtle syntax is what you do is you define up front these namespaces. So you're basically saying vcard, that's actually a public one, and then you point it out to a URL here where you can actually get it. Right, so there it is right there. It's at that address. And then we also have CPH here. So what we'll do is when you're actually building one of these things up, you'll actually use your own namespace that you define on the side. All right, so here's the first triple. And there should be periods after these, by the way. I'm a little bit of problem with syntax there. All right, so the first one here, the first triple is basically it's a triple, because it's just going to be spaces are going to separate the components. All right, so we have subject is CPHMM, right? Whatever that is, that's me. Okay, so it's going off to the let's see if I don't know if you guys can see my pointer. Probably it's going off here to the to this definition here where we have defined the name MM, and so it's saying MM, fine, and then it's going to vcard. So vcard is going off to this one here, and it's basically saying the given name is Michael. So the MM URI has a given name of Michael. So we've associated via this predicate given name, we've associated the subject MM with the literal Michael. Okay. And then we do the family name, and then we say the title okay. Now, finally, what we're seeing here now is we're going to get into a object, which is URI also. So we're basically going to say here, we will say that the MM has the role of CEO. Okay, now notice here the title CEO and role CEO. So it's a little bit redundant there. We've kind of I've added in a little bit extra information. So it's starting to get a little sloppy. All right. So, but you know, I hope that you guys kind of track what's going on with this. Okay, then works at. So that's an also I defined a predicate works at, and then I also define a predicate serves. So these are all corresponding to these. These are corresponding to these triples up here that I wrote just conceptually the triple. Then there's the higher date literal. Okay, so you can imagine just having in this turtle syntax, just specifying a whole bunch of this stuff to define a graph, right? I'm defining this graph that represents the information. Okay, now once that's, so let's assume that we have that triple, these triples, and then, well, how do we query them? So there's a query language now, Sparkle. And what Sparkle does, first of all, you have to kind of bring in these these namespaces, and it's kind of like SQL. But let's take a look at what it does. Okay, so what does this query do here? Let's just take a look. All right, so what is this query doing? All right, so it's going now. The things that are prefaced with a question mark are variables. That's how variables get. So we're selecting two variables, the first name and the last name. So we're getting the names of people, right? And it looks like the first name has to be, it's going to bind with a person, that's the given name, and the last name is the family name, right? And that person, we're putting more further constraints, that person has to work at CPH, okay? So you have to work at the company. And then also that person has a hire date, all right? So we have the variable hire date here. And now that hire date has to be less than 2020. 0101. Okay, so it has to be before 2020. All right, so that will work. That will work over that okay, it's called a triple store. All right, so those triples that were specified in turtle syntax are going to get shoved into a triple store, which is essentially a database, right? It's just a database with one table and 3 columns, right? It's just going to get shoved in there, and now we can actually solve this query with Sparkle over that triple store. Okay, so I hope that's kind of clear what's going on there, right? So triple store. So this is over, essentially this is over kind of a limited representation where you just put everything into triples. Okay. Now, if we talk about, let's go to a kind of a classic n-ary relation in relational databases. So this n-ary relation is basically this the suppliers supplying a product to a customer. So, and then we have also, I put in the year in which it's happening. So we have the notion of IBM supplying DB2 to SEB. I've said this is okay. This is just kind of, this is an n-ary table because it's not a table where we just have 3 attributes. We have an arbitrary number of attributes in the table, arbitrary number of columns in the table. This is the thing. Now, what the people that do RDS say was, I'll say that, well, we can represent this. We can represent this. So, and I think that the argument is this. The argument is that then, therefore, triple stores are representationally equivalent to n-ary relational databases. That, I'm afraid, is a pretty, that becomes, as a practical matter, logically, that's not, now, doing reification, which is this idea of thingifying. So if you go to philosophy and you hear about what reification is, so this is a term that gets used in logics. So to reify means to thingify something. So the way you can actually reify this relation, or you can reify this table. So when you say reify the table, what you mean, first of all, you're going to make an assumption that tuples have identifiers. Okay. So you're going to put the IDs 1, 2, and 3 on the tuples, right? There's no other way to do it. You have to basically make that assumption. Now, that actually is a step that you're making there. Traditionally, relational databases are said to be value oriented, not object oriented. Putting these IDs on things actually goes into an object orientation. So it's actually kind of fiddling with the semantics of what of relational databases. But let's let that happen. Let's let that go ahead. So then what you would do then is that you basically are going to basically then assert a new type, a new URI, if you will, of IDs of this particular table. Let's call this the supplier table. So we're going to come up with a new URI or a new type of thing called a supplier ID or a supplier table ID, right? And then what we're going to do is we're going to make a triple that says something like this. We're going to say this ID 1 is going to be the subject. Then the predicate is going to be supplier, and the object is going to be IBM. So we're going to get one triple there, another triple there, another triple there, and another triple there. So we're going to get 4 triples to represent this one row in this table. Okay, is that clear? I hope that's clear. I mean, I could make a graph here, and I could do like a bunch of fancy graphics to show that, but it should be clear kind of what I mean by that. Likewise, here you're going to have 2 as the subject, supplier as the predicate, and Microsoft as the object. So you're going to get, in total here, we're going to wind up getting, we'll have, all right, we get 1, 2, 3, 4. We're going to get 12 total triples. All right. So you can basically squash this thing down into 12 triples. Right. Okay. Now, these, and then you can go and you can put these into a triple store. You can put these into a triple store type database. All right. Now, that triple store, by the way, just as an aside comment, just to relate this back to our earlier discussions. If you're going to do this in this triple store, you definitely want this to be a column store rather than a row store. Right? It's just going to wind up being a lot more efficient if you do it that way. And you can think about why. All right, but let's say we do that. Okay, let's just, I hope you can hold this in your mind and see those 12 triples. Now, if you have those 12 triples, then quick, write a query that says that give me the companies that were supplied by Microsoft after 2015. It's good, you can do it, but it's going to be a tricky query and there's going to be a lot of joins. You're going to be doing a lot of joins. How are you going to do this? You're going to basically say, well, okay, now I have to find all the triples that represent, look for an ID here. I have to find all the triples that represent Microsoft as the supplier. And then I have to find all the triples that have a year that's after 2015. All right. And then I have to also find all the triples that basically are, that correspond to those triples where I have to find all the triples where, of those triples that are the intersection of those two sets, where the customer, where there's a customer, and then I have to pluck out the customer ID there. Okay, so that's getting kind of complicated. Now, if we were going to do joins here, where we're going to basically join and give me the CEOs of all the, where we have another table, it's going to get even more complicated. All right, it is doable technically, but it's getting pretty hard. And the thing is, if you're going to do anything like aggregation, it's going to be really hard. So is this really up to the power of SQL? No, it isn't. Not if you're going to do the full kind of grouping aggregation. It's just not going to, you're not going to be able to do it practically. It's going to be a problem. So that's a little bit of an issue. So there is this kind of limitation in the basic semantics. All right, so so this right here is just getting us to this point here. One sec. This right here is just, this was RDF. That was RDF model and syntax. Now ontologies are going to sit above that, and ontologies are going to put like certain definitions that, again, they're essentially like a view over that triple store. So you could say something like this, like give me the, like let's say give me the companies that have exactly 14 employees. All right. Right, you could specify that. Give me the companies that are doing that are supplying IBM. You could define that too in this, in essentially this an expression in the Sparkle. Now, the ontology languages themselves are a bit more complicated than that. They're very, very syntactic. But the thing is that you can, one of the things you can do with them, which is the kind of the big claim to fame with them, these actually derive from something called description logics, which again is a concept that goes way back in the day that comes from an extension to semantic networks, or something that kind of is over semantic networks. What you can do is you can do basically what's called a subsumption calculation. So is it the case, for instance, that if I say something like, give me all the, I define a concept that says the companies that supply more than 3 companies in the industry of tech. Is it true always that that subsumes, that set will be a superset of give me the companies that supply at least 4 companies in tech where the subgroup is biotech or something like that? Okay, so if you think about the logic, actually it's true that you can wind up doing a calculation, a priori calculation over those kind of concepts defined in what's called an ontology, and you can basically induce this kind of set of containments that work over the concepts. It's a nice property to have. The database people have kind of done something analogous working with query containment. But the issue is that it's a nice property to have, but the question is, what does it really do in the world? That's one of the things. It gives you something, but what really to make? I mean, people have to justify paying for these things, you know. So it's a little bit the semantic web. I'm sure that if this gets shared at one point, this video gets shared, I'll get an earful from the semantic web people. But I mean, those guys have been working on it for like 20 years now. Maybe 30 if you include, or maybe 40 or 50 if you include going way back to the research roots. And it's just, it does not have the legs that SQL has. Let's put it that way. It does not have the legs. I mean, how many people are using this stuff? This ontology, this OWL stuff. I mean, some of the big companies are doing it, but they're doing these kind of big, kind of heavyweight projects where they're funding all this stuff. And the question is it really getting traction? And I think the answer is no. But my opinion. All right, so on the semantic web, let's just talk about it because I don't want to poo-poo it too much, but yeah. All right, now argument, I'll lift them up a little bit and say this. Semantic web, all right, the idea of just having like this giant source of all this data out there, web-based data out there, and then doing meaningful queries over it to get information back. Now, in one way, I mean, that's arguably that crawling the web and bringing in web pages and all that, and then PageRank, they're arguably in that spirit, because it is arguably turning the whole web into a database that you access, right? So, yeah, that's true. And it's what's nice about it, of course, is it doesn't require anybody's collaboration. I mean, honestly, if you require people's collaboration, it's not going to work. People don't collaborate. I mean, they collaborate a little bit. They want to a little bit. They certainly say they'll collaborate, but do they? I mean, why do people collaborate around the web? It's because HTTP and HTML were so simple, right? And you could just do it on your own, kind of in a decentralized way. And you could plug it in, it would work, and that's great, okay? But when you start talking about these ontologies and all this kind of complex stuff, I mean, all right, so anyways, the semantic web stuff started in the late 1990s. So the main, the W3C, World Wide Web Consortia, is the main standards bodies. URL, okay, so basically I would say URL, URI, yeah, they're great. Okay, that's great. XML, yeah, it's pretty good. Yeah, it's great. RDF, all right, maybe. XQuery, XPath, yeah. I mean, they're we cover them in the course. I mean, they're not getting used that much, but you occasionally see them getting used. XML schema, Sparkle, yeah. OWL, and then there's like 1,000 other ones. I mean, there's some good data sources that have kind of plopped out of this stuff in a way. I mean, this whole DBpedia, there's of course Wikipedia, then there's DBpedia and Wikidata. A lot of things are building on top of that. And then you have Google's knowledge graph, which is kind of interesting. It's a graph database. So it's basically doing like the semantic network stuff. I don't think they're adopting RDF though. I'm not really sure. I haven't looked into it too much. But things that are kind of like lots of kind of just like almost common sense knowledge, common sense facts are encoded in this thing. So it's a giant graph that they've kind of brought in from all these different sources. And that can be useful. I can see people using that. But the semantic web, I mean, it's an admirable vision, but very challenging. So imposing workable semantics across the web is very difficult. And then it's difficult to actually work, especially with the ontology technologies and standards. So one of the kind of things that you see sometimes people when they criticize it, they say it was written by PhDs for PhDs. And that's just not gonna work. I mean, you know, it can't, you gotta make things simple. It's got some problem with scalability and interoperability. And then of course the alphabet soup of all the standards. And then also, I think I talked about this a bit, semantics based on triple stores plus reification is actually kind of weak and unworkable, uncontrollable. I mean, getting deduction, that is like kind of like, you know, sound and complete reasoning over that kind of scheme is going to be really hard. But more power to them if they get to work. Okay, so anyways, are there any questions about semantic web stuff? That I'm just going to conclude it then and just say that, okay, well, it's great if it ever worked. Sorry, I shouldn't poo-poo so much. All right, so then let's go to plan B here. All right, plan B is basically just like ingesting data from the web or whatever sources you have into your private database. All right. So it's more decentralized, where organizations ingest the data into their own databases for their own purposes. So there is a reason why they're funding the project, and that's what's guiding it. You know, they're doing it for a reason. So it relies on a mix of what's kind of, I break these things down into three basic techniques. Data exchange, which is taking data from other structured sources. Data extraction, which is basically pulling data out of no structures. Or very low structures. And then there's a third way, and that is like the bulk loading of the no structures into the database. So you're going to bring them into the database, and then you're going to do a search over that using SQL. So it's not necessarily based on relational databases, and people could probably do this with like document bases, like you could do this with Mongo or something. But the assumption here is it's going to be relational. I think most of the time it is relational. Okay, but again, I mean, there's no need not to be web friendly. So I would certainly, the whole idea of the way you're going to bring data in data exchange and data extraction and bulk loading, like most likely you're going to be sucking stuff off of the web. I mean, you're going to be using URLs to go out and grab stuff and request it, and then you're going to bring it in. So there's always that. And then also the data that you store, there's nothing that says you can't take advantage of URIs. So to have, to have some kind of consistent naming scheme or constant scheme, and also URLs, so that that your application, people when they use the application, they can click on stuff and then kind of go off and navigate to websites. All right, so that's absolutely going to be part of this as well. So it's not like going way back to like zero web. There's definitely a lot of web stuff in this, but again, it's more under a kind of decentralized and more private application of this. So here's a graph to kind of show you this process. So it's like, okay, so basically in our database, in our relational database here, we have what I've distinguished two different types of tables. There's a model table and there's a document table. So a model table would be a table where you're actually going to have facts that you're modeling inside of your conceptual model for the database. So in this case here, if like you were going to have, so for instance, you're going to have, let's say, stock prices at particular moments, that would be modeled data. So if you're doing any kind of exchange or extraction into that, you would be you'll be doing something that you're going to query directly on. The document table is real simple. The document table is you're just going to suck in a full document. You're going to just pull it in, all right, and you're just going to have it as a giant character large object, a clob that's just sitting in your database table here. So data exchange is going from kind of relatively structured things like relational databases and CSV, so common separated files, which like Excel or Google Sheet type files. Those get brought in via data exchange into this model table. Data extraction is something where you're going to go through and you're going to like pull in, you're going to have something that comes in as text or HTML or as a PDF or something, and you're going to go and you're going to have external programs which are going to go into that, and they're going to kind of go and they're going to find particular data values in there through an extraction, and then they're going to then formulate an insert query where they're going to actually push that into the model table. XML and JSON are kind of in between, they're kind of as semi-structured. So a lot of times the XML or JSON stuff, actually you're going to use data exchange type stuff. And I'll show that in a second about, kind of some of the common libraries you would use to do that. The bulk loads are just going to, you're going to take you can do a bulk load of XML and JSON as well. You just do it like, basically you're just going to take the full contents and you're going to dump them into a cloud. All right. So what are we going to cover? And we're going to cover this next hour. Data exchange, we're basically going to cover that. And we're going to notice like the centrality in data exchange of XML and JSON. All right, so JavaScript object notation and XML are kind of central. These are kind of the central representations of data exchange. I mean, you can have a data exchange in a different way. You can have a data exchange where I actually have an SQL interface to one particular database, and I'm going to launch SQL queries over that, bring them into my program, and then take that and then insert that into my centralized private database. Yeah, that's one also. But the thing is that a lot of times that's not really the way it works anymore with REST calls and stuff like that. You do a REST call, you get back a JSON object, and then you take that and you navigate that and you put that into your database. That's more of a common way things get done these days, because REST is so much easier than hooking up all the database stuff. But there's lots of different. These are always specialized to whatever particular purpose. But in exchange, we'll take XML and JSON as kind of the central kind of representations. In data extraction, then there's the centrality of regex. So I'm not sure how many of you guys have done. I mean, you've all seen regex, but what I want, and we're gonna do this in recitation number 4, is I really want you guys to kind of get a real handle on regex, because this is so useful. Regex, and it's kind of like a query language in a way. So it's kind of, you can kind of frame it in database-like ways. It is a query language essentially, and I just think that you guys should really be up to speed on regex, because this is if you don't know regex, then you start doing this kind of stuff, that's really bad. So I want you guys to know regex. So recitation will be around that. Bulk data load, again, in bulk data load, centrality of regex, but it's regex used inside the database, right? So you're going to bulk load the stuff in, and then from SQL you're going to do regex over the loaded in data. Okay, so that's kind of where regex also comes in. So we see the centrality of XML and JSON. I'm not going to cover those so much because they're so easy. But regex we're going to cover. And then I'm also going to talk a little bit. Unfortunately, I didn't get too much of a chance to kind of develop slides on this, but just the whole kind of emerging role that natural language processing technology is having with respect to this, because that's something that is going to improve a lot of this stuff and maybe make it more automated. Okay, so all right, so we're going to cover that next hour. So I think now let's just do it as we were saying before. Let's take our 10-minute break. Okay. Are there any questions? Okay, I don't see any questions. So, okay, we'll take our 10-minute break and then we'll come back and finish this up. And I will stop share, and then I will pause the recording. All right, So I think we can resume now. So data exchange, data extraction, and this bulk data load. So data exchange, this, kind of borrowing from data warehousing. So external programs, ETL, extract, transform, and load data from structured data sources. It's fairly straightforward. The thing is that I'm going to just talk about external programs. So generally speaking, you write this outside of the database. You don't want to do server. I mean, you could maybe do it outside the database. Well, I just assume people are going to use Python. I'm sure there's equivalents for Java and all the other languages, but Python is really good actually. Pandas, there's just kind of some just standard stuff that will convert CSVs. So CSVs get extracted from Excel or Google Sheets, and then you can put them into data frames and then pull out JSON and then pluck it on over to your database. So it's pretty straightforward. JSON, so if you do REST calls, so REST calls, you're going to make calls into the APIs at different endpoints out on the internet. So a lot of places will give you API calls in, so that they'll do it as a REST interface. And I'm assuming you guys are all familiar with this, where you just you pack the parameters on the like the get request, and then it'll throw you back JSON or XML maybe, but JSON. So when you get those back, so basically it's something, you get something that looks kind of like this. You're going to put using this request library, you're going to basically get the response. You're going to pull off of from a URL. You're basically just going to put it in there. Now this headers thing, I'm sure that some of you guys who have some scrape experience know that sometimes you have to kind of make the headers right and make it look like you're a human, because they don't want you in there scraping data. But this is part of the business. So there's a whole kind of thing. Another thing also is just to find out, like you go to a website, there's a form there. You have to kind of go into the console and kind of like look around and find out what are the actual calls being made out to some REST interface. Then you spoof that, and then you have you copy the headers that are there, and then you can grab the data. So there's basically data exchange that's willing, and there's data exchange that's which is a scrape. So yeah, you guys are on your own. I don't know. It's part of the wild west of the internet still. Anyways, you get the result back, and then you do this JSON load. So basically, you can just kind of go through the JSON. So it's really straightforward. So DOM objects represent XML files can be walked in. So basically, a lot of times what you do is you wind up here's an example of grabbing from System Belongit. So you basically pull in the URL, the data from the XML. You can do this every day. They're going to publish a new one for System Belongit, and then you put this through the you parse it, you do an XML parse, and then once you do that, then you can kind of walk the tags, and you can scoop up the data, right? And you do that, and then you insert it into your database, right? So that's data exchange. There's a lot of other, there's 1,001 different ways you can do data exchange. Data extraction. So so when you're doing PDF, when you're extracting from PDFs, this is very common that you get a whole pile of PDFs, or you get you get pointers to links out there of a whole bunch of PDFs that you're going to then go and just going to pull in. Once you get the file, once you actually get the PDF file, save it off as a PDF file, you can do a textract, which will actually pull the text out of the PDF file. And then let's say you do that. Let's say you grab it, you have you have 1,001 PDF files, and you want to scrape information from them, or you want to extract information from them. Then what happens is you just get the text for that file, and then you do stuff like regex. So in this regex here, we're looking for all the years, which is like this, which is a DDD to a DDD. All right, that's just happens to be how it is, and we're gonna get the very first one that's in the file. So basically, that's using regex to actually pull out and extract a chunk of data that can then be part of an insert statement. Now, this is something that just to keep in mind if you're doing anything with PDFs. If you get table data in the PDF, you want to get that out with Tabula. There's a different package called Tabula, and you can get that out in JSON format. in principle, you could actually get that information through the text, but you don't want to do it that way. You want to use tabular. All right. Now, I think a lot of you guys have, well, many of you have experience now with something like beautiful soup. And there's a Java variation for beautiful soup. But the idea here that basically with beautiful soup is you're going to be, when you're actually extracting from HTML. So with HTML, you know, you go in and you basically have, you get the page HTML from, you know, just requests and pulling the actual data over. And then you put it through the soups parser. And then once you do that, then what you can do is you can actually go through and you can do these kind of, on the actual soup representation, you can do stuff like find, you know, this is like the element, and then here's something that, some conditions on the class. So you can put different queries here. So they're basically, they're going and they're searching for different elements, HTML elements. And then from that, then you can maybe get, from that, you get the details here. And then from that, you can extract the text. And that'll give you the snippet. Now from that snippet, you might want to then do regex to actually pull out the actual data. Right. So these are just kind of in Python, at least, how you, some of the kind of like the little, you know, plumbing stuff that you do to kind of do a data extraction. Now with bulk load, whole documents, PDFs, yeah, are basically loaded directly into the database. Now when you do that, you're going to bring all those into the database, and you're going to basically search via SQL using either regular expressions or what we call full text search, which PostgreSQL has a package developed for that. And we'll go over that quickly today. And also another thing just to keep in mind is that when you do the full bulk load, a lot of times you'll also run other external programs that'll do stuff like sentiment analysis, or do they'll do further computations alongside the bulk load, and then it will associate things with. So if you're doing sentiment analysis, like for instance reviews of restaurants, you're doing bulk loads of all the actual texts that are restaurant reviews, then you would also then run the sentiment analysis at that time, so it's all pre-computed, and then you can put in the value judgments alongside, you know, in the particular table, particular document table. Okay, so that's just kind of how you do the practical. All right, so that's fine. That's all fine and good, and that's just kind of some indication, maybe some just mentioning if you're using in the Python ecosystem, mentioning some of the important packages that do this. Now, let's go on to regular expressions. So, because down at the base level, you're going to be using regular expressions to kind of extract out the actual data values. All right, so regular expressions. So the initial ideas behind regular expressions were developed by Kleene in the 1950s. So I'm not sure how many of you guys have had like theory of computer science course, but this whole thing about finite state automata and regular expressions and this kind of stuff, where you have basically the Kleene star operator, the plus operator, and what else do you have? Just kind of concatenation and disjunction. These are kind of like your main kind of elements in that regular expression language. But that's really, really simple. That's really just, it's more of a theoretician's kind of toy. Real regular expressions from a computer science point of view, they're basically, you know, the practical extensions and everything comes around with early Unix work. All right. And then there's slight variations, but essentially this has all been standardized in POSIX. So POSIX regular expressions are kind of the ones that we use. So both Python and PostgreSQL conform to the following two slides. So works for both. Now, unfortunately, you get small quirky variations in the different implementations. I don't know all the details. All I know is that that at least in Python and in PostgreSQL, the following works. The following is exactly the same. So let's just kind of go over some of this. Again, I'm assuming you guys have seen this stuff before, but why not? It just bears repeating. So basically, the way regular expressions work. There are a regular expression, of course, is an expression, and that expression then is going to run over or be interpreted over an actual piece of text, all right, a string. All right, so the regular expressions, we build up these expressions, and then we can apply these expressions and get behaviors over a string input. And that string input can be just, you know, any arbitrary string. And so regular expressions are defining essentially an infinite number of input-output pairs. Right. So, but there is always going to be one specific output. Given a string and given a regular expression, you're always going to get one specific output. All right. So the way these things work is we have like the dot, which basically match any character. So let me see if I can bring something in here. We'll get to this in a second. So when I do some examples, the up arrow matches the start of the string. The $ matches the end of the string. Star, if there's a preceding regular expression, star basically means 0 or any number of times of it. Plus basically means 1 to any number of times. A question mark means the preceding regular expression, 0 to 1. And then we have these ones where we have a star question mark, plus question mark, and a question mark. And these are all the non-greedy variations of the star plus and question mark. So by default, regular expressions are greedy. So they'll try to consume as much of the string as possible when you apply them. All right. So, but if you want to have the non-greedy, which will try to just consume the least amount possible, then you just have to use this question mark. Bracket m will basically give you, it's going to match that many times. And then this gives you a bounds, m to n. And then there's a non-greedy variation. So this is kind of, Backslash escapes these special characters. So if you want to match like question mark, you have to say backslash question mark, because question mark is reserved, right? Brackets indicate a set of characters. So A, B, C, D means match A or B or C or D. And then the one little thing that kind of gets people is that the special characters, all these characters, they lose their meanings when they're inside these brackets. Okay. So up arrow at the beginning basically complements the whole set. So this basically will match anything other than A, B, C, or D. Right? That's what that indicates. Okay. The vertical is a or, and here's where it gets kind of interesting. So the open parenthesis, close parentheses, what they do is they mark the beginning and end of a capturing group, which then gets placed in a register, right? Which actually gets saved off to the side. These groups can then later match with a number. Okay, so you don't do that too often, but you can. Right. So that's basically a capturing group. But if you want to do a group that's not capturing, which comes up quite a bit, is you have to say open parenthesis question mark colon and then whatever is going to be in the group there. This right here will match the contents of an earlier register. All right, whichever register was it's like \1 will give you the first register. All right, or \0. These kind of just could memorize these. So D matches a digit. This matches a non-digit. When you capitalize it, it's kind of funny, but you capitalize it, matches the complement. This matches any white space character. So space, carriage return, new line, all that stuff is matched by a backslash lowercase s. And this matches any non-white space character, anything other than those. Backslash W matches any word character, so any non-space character that's part of a word. And then this is any non-word character. Okay, so these, you'll just see these kind of all over the place. All right, so using regular expressions. So in Python, for instance, we'll just kind of look at an example here of what's going on in Python. So if we use the find all, what we get here is we have, we're going to be looking for a capturing group where it starts with an M character, then it has any number, greedy, so it takes as many as possible of word characters, so non-space characters, and then an E, okay? And then after that, if you notice, there's a space there. There's another little space there, okay? Now, if you run this over Greg, Michael, Mike, Martine, and Billy, so in words, what this is doing is it's capturing everything that starts with an M and ends with an E, and also has a space following it. So that is going to mean Michael doesn't fit, no, but Mike does and Martine do. So basically what's going to happen here, because it's capturing it, it'll bring you back Mike and Martine, okay? So again, if you don't, I mean, I think that probably a lot of you are probably rolling your eyes and saying, yeah, we've seen this, we've done this 1,000 times. So, okay, fine. But for some people who haven't, yeah, I mean, so these things can get a little bit tricky, and you'll see in recitation, I'm going to just line up a whole bunch of these things, And you guys are going to have to be able to kind of write these kind of expressions, and you're going to have to know all of these. You're going to have to basically, I'm going to write things that use all of these. Now there's the look around operations, and I was going to put those in but I didn't have the time to add it to the slide. But yeah, I'll put in the look around also. So there's these look around, sniff ahead, sniff back type regex. Yeah, it's worth knowing those as well. So okay, so that's regular expressions. So in PostgreSQL, we can also use regular expressions inside of PostgreSQL. So we'll do that. We'll just describe that here now. So in SQL, we have the like and the I like. So I like is just, so the like operator, if you remember, like operator has just like, it's like what came with like original SQL, and it has like the percent sign stands for the star essentially, or any number of characters, and it's like stands for the dot star in regex, and then the wild card stands for like the single character, like the dot question mark. But that's a bit too simple. All right. So this, yeah, I mean, but it's nice in the sense that it does, there's no security problems. There's no problems with like, people doing kind of injection attacks or anything using like. There's potentials for in regex, but we'll ignore that. The SQL 1999, so the big standards in 1999, proposed similar to, which was using kind of a POSIX-like regular expressions, but not quite. So we're going to just go right to the POSIX compatibility. Let's use that. So the tilde in PostgreSQL will give us that. So in So in PostgreSQL, let's just assume now that we have the following table in PostgreSQL, where we have just a bunch of content. So in fact, actually, if I can do this here, I hope I can. Listen, control plus plus plus. Select content from doc. All right, yeah, there's a bunch of junk here. So I pasted in a bunch of like articles from just from Yahoo News, Yahoo News. They're all in there. So for basically say, what are there? I think there's only 8 of them. I just did this kind of really quick. So there's these 8. All right, fine. All right, so we have 8 of those in there. So we'll actually be able to do a little bit of demoing here. So if I basically take this question, select ID from doc where content matches the regular expression trump. So all right, maybe I can do this a different way. One sec. All right. I'm just going to get this because I don't want to type this in. I want to just paste it in, and I'm going to do it the following way. One sec. Give me a moment. Dun, dun, dun. All right. Yes. All right. God only knows if I'm saving time here, but at least it'll be a little bit less error prone. Yeah, here we go. So, unfortunately, I have to do it this way. Good. All right. So if I select ID from doc where the content is trump, that's basically, here's a regex with trump. So I could do something like this. I could say, what about that? Yeah, so it'll match that. And then if I say that, it might match more. Let's see. If I say RU, where content is th. That should be all. Yeah, because of the, right? So if I say, so basically we can put in any kind of regular expression we want right here. Let's see. So if I say something like Biden, Trump, all right, nothing. And the reason is because it's case sensitive. So if you do this right here with a star there, that makes it so it's case insensitive. Okay, so there we are. So if I then say here, here's another example that shows a bit more of, shows a capturing group, which is going to be kind of nice. So edit, paste. All right, so what is this saying here? So now we're going to use this thing called the substring. So it's going to go into the content, right? So that's the content of these articles. And then from that, it's going to basically grab up the first group that's specified here. So a group here is Trump. And then, so what is this actually doing here? Let's think about this for a second. If anybody could answer in the chat, but I guess no one will. What is this thing actually doing? Well, what it's doing is it's basically going to grab every sentence that it's going to grab everything to the end of the line, because this up arrow here means complement, which is not a dot. And dot here has lost its meaning because it's inside the brackets. So this is going to basically give us, okay, Trump tweeted that. So this, because everything that's going to go to the end of a line, campaign Trump, okay, these are, that's essentially what's going to happen. So that's using regex to do that kind of thing. So you can't do that with like. All right, no, you can't. You need to have regex to do this kind of extraction. Let's see here. Right, I'll move this guy to here, and so these are just those examples using regex. Oh, here's another one. Okay, so here's where we're using an actual replace. Okay, so what this does. So if we look right here, we see that we had all this, that Trump tweeted, blah, 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 all that stuff. Now, if we want to do the same thing, but we want to, in place of that, we want to, instead of using Trump, we want to use the expression, the orange one. Let's paste this in. Then basically, now it's going to say the orange one tweeted, the orange one parroted. So we can actually do some manipulation there. So what this is doing here is it's doing a regex replace. So it's getting here the substring. It's getting that same thing where we're getting the actual line there, and then what it's doing is it's going to replace Trump with the orange one, and yeah, so we get to that. So you can do a lot of sophisticated things with regex. Just with inside of PostgreSQL. Now, there are certain things you cannot do, and that's where we get into full text search. So with full text search, sometimes we need more support, linguistic support, than we get just through regex. And through this, we can essentially get close to implementing what we call kind of classical information retrieval, which is the case where the document is the basic unit and you're doing kind of Boolean and ors over content. So we'll show that in a second here. So if we say here, so now if we basically say this, now the way this works is the following. So we have a new operator, which is this double @ operator. And what it does is it takes in a text search query and it takes in a text search vector. We'll show what those are in a second. And it does a match. So this is basically saying Trump and president. Okay. So give me all the IDs of documents where the document contains both Trump and president. All right. Let's see here. And then we can have a little bit more sophisticated. I'll do both of these. What the hell? Let's see. What did I do? There it is. So these are the IDs of the documents. So these are documents where basically we're having both Trump and president. All right. And then this right here, and notice this is case insensitive, right? So tr ump, and then just to verify this thing works. This was ID, this was with Trump and president was 1 and 4. And now if we actually have Trump president and does not include tweeting. So there's no mention of tweeting or tweet or tweets. So that's that's good about this stuff is it computes these lexemes, and I'll show that in a second. Anyways, we can have these kind of Boolean expressions here, and we are running those over this over the content here and getting. So this is the only document in the set that has Trump and president, but does not mention tweeting. Okay. All right. So let's kind of look a little bit more into what's going on here. Okay. So so let's talk about what actually happens to the content when we're going to do one of these text search queries. So the first thing that happens to the content is it gets tokenized. So when you put the string in, it'll get tokenized. So tokenized means you split it up based on white space. So you turn it into a string of words. All right. Now these tokens or words are converted then to lexemes. So this is using a language model. All right. So the language in English, I mean, there's kind of suffix rules that you have, so you can strip things off, and we'll see that in a second. And then we also have stop words like and, things that we don't want to count the number of, that we just have determined are so common they're irrelevant, like some of the common function words in English. And then we also retain location information. So if I do the following, just to kind of show how this gets calculated. So if I come over here and I say the following query, edit, paste, wait. All right, so here's the query. Sorry. So we're just going to do it right here. So I say basically, I say I'm going to take the string in. This is the I'm going to convert this to a text search vector. All right. So this is going to do this tokenization, dropping of stop words and location and retaining location information. I'm going to do all this right here using the toTsVector function in PostgreSQL. So if I have the string I'm putting in is King Kong Bundy was a great wrestler. It is sad that he is no longer with us. You rock, King Kong. Rest in peace. All right. So if I type that in, then look what happens here. First of all, Bundy gets lexemed down to Bundy, so it's kind of weird. But anyways, and then the location for Bundy is recorded here. Great restaurant. That's fine. Doesn't get lexemed. So these are alphabetically ordered here, if you notice. King, as in the King Kong, is at positions 1 and 20, and positions meaning that number of words into the document. And then Kong is at 2 and 21, longer. If you recall, I said you rocked, but it's lexing that down to rock. Sad, you with us wrestler. Okay, so that's what it gets converted into. So that's kind of the compact representation that is going to be converted into that allows you to both recover the location information and also allows for a little bit more flexibility in terms of the text search. So with lexemes. There is a Swedish model too, so if you can use that one if you want. Likewise, always keep in mind that the same thing is happening on the querying side. So when I say this query here, so when I turn the search query, in this case, I have the query Trump and president, but there's no tweeting or yelling in the document. That gets reduced to this. All right. So if you notice, president, this is where it's kind of a little bit like, all right, that's what it does. It winds up. So tweeting gets turned into tweet, and yelling gets lexemed down to yell. President gets lexemed down to president. So But anyways, it's going to get lexing down to the same thing. You're using the same converter on both the source text and on the query, so there'll be a match, right? So you'll get a match if when text search does its stuff. All right. Okay, so it's nice. It's a nice capability that's in there inside of PostgreSQL. Definitely worth considering. All right, now you definitely want to use indices here for this kind of stuff. When you get a huge document base, you're going to want to. So if you get a, if you're going to have 200,000 documents, you don't want it to be calculating. You don't want to do it this way, where you don't want to do it where you're actually be doing. You're going over content. You're doing a table scan, and you're doing all the conversions to the TS vector for each data item every time. That's not, you don't want to do that. So you want to create an index. So you can create this index, basically this general inverted index, or this inverted index. And what this is going to do, it's going to basically it's going to create this index I content on the document using, and basically this function here, where it's going to go over the content. So that'll build that. Another way you're going to do it, which is going to make it a little bit easier, is you just store it alongside. You can just pre-compute it, and you can store the index directly in the data, or you can store all the pre-computations inside the database. So you can have an extra column called TS vector. So if you do basically this, explain analyze on this right here, you'll find it takes 6 milliseconds, and then if you do it where you actually put in the index, you put in the actual index pre-calculation, that's like much less. But this is just over 8 documents. I need to put more documents to get it so that PostgreSQL actually uses the index. Well, it uses the index. It has to scan everything. It's gonna use the index at every step. But I haven't really got. I need to kind of. Well, this right here shows that if you pre-computed it, it's gonna go quicker. It'll be interesting to see in recitation if we can kind of establish that we're really getting these indexes used. All right, finally, there's a kind of something that's a little bit problematic in this stuff. So this is a little bit not really state of the art in terms of full text search. It's just kind of really basic, bare bones. It's inside of PostgreSQL now. Maybe in the future that'll change. I'm of the opinion that everything eventually gets pulled into the database. So I don't know what other databases have in terms of these kind of capabilities, but what we have here is we have just a very simple way of doing ranking. So we have this Boolean model, and what we can do here, so basically what does this do right here? Select ID, and now what I'm doing is I'm basically summing, there's this thing called TS rank, which essentially counts the number of the term frequency. How many times is Trump being found inside the document, essentially, or some kind of weighting on that. There's a bit more you can do with rankings, but it's all a little bit non-state of the art inside of PostgreSQL. But if we look at this, at least this query here, let's just do this. If I'm looking for Trump inside this 8 document base, if you recall, there's only 2 spots he's at. Here, let's see, 2 documents he's in. And here we go. So there's 2 documents he's in, and I just ran the query here, so I'll show it. It's ordering by rank here, by score to get the rank. The rank is document 1 comes first because there's 2 mentions of Trump here, and there's only 1 mention of Trump in this document here. Right? Okay, so this is kind of just a way you can kind of get a little bit of that ranking going on, but unfortunately the ranking stuff isn't very well developed inside of PostgreSQL. I don't think they've changed the full text search for many versions of PostgreSQL now. So I don't think it's dead, but it would be nice if they could bring stuff in. Because the true story with ranking, modern ranking, actually is not just this Boolean model. In modern ranking, you have like vector space models. So what you do is you go and you to rank different documents. So this is more to calculate similarity, but you can do it also do it over the term searching, you basically calculate the cosine differences between different documents. So basically, all these documents, the presence of words, defines this gigantic matrix of this gigantic multidimensional vector. And then the question, you take two different documents, and then you compare what's the angle in that multidimensional space between them, and that gives you some kind of measure of similarity. Also, I mean, you're talking like other different ways to do PageRank, where you have like kind of voting by how many references to a page to kind of indicate its quality, like PageRank. This stuff you can't. It's not even hard. It's not even clear how you would integrate that in. But this stuff is all this more sophisticated stuff in information retrieval is kind of missing in full text search inside of PostgreSQL. Okay, so yeah, it looks like we're going to be able to finish here. Just, this is unfortunate, I didn't really have the time to develop this so much, but there's a lot of interesting stuff going on in how natural language processing is going to contribute to this kind of work. So in text extraction, so so we have the notion of text extraction, or this data extraction. So what that means, it means that, like, let's say, for instance, we have a very structured representation we want to reach. Let's say that talks about all the different engagements of the Roman. We have this giant text source, which is Gibbon's decline and fall of the Roman Empire. And what we want to do is we want to basically pull from that data that talks about different territories that the Romans conquered at different times, and the reigns of different Caesars or emperors, and at different time spans, and maybe some other kind of developments in society, like certain inventions and stuff like that. So we kind of know what we're looking for. We want to populate a giant database with structured information that gives us kind of something we can query in SQL that's somewhat complete, that gives us a full record of the exact facts that unfolded in history of Rome, or the decline and fall of Rome. That is a text extraction task. Okay, so that's going to be really hard, right? You're going to have to. That's very natural language oriented. Now, there's a whole story about different ways and techniques you can do this. This has been tried. This is very classic NLP problem. So NLP is tough because you have as you're reading these things. I mean, one of the main problems with NLP is you have anaphora. So anaphora, what those are pronouns essentially. So as you're going through, you're hearing that. So Gibbon's developing, talking about what happened to let's say Maximin, one of my favorite emperors, by the way. Maximin is you should read the story of Maximin. So Maximin and how he transitioned in and out of power, and it included death in both cases, on the way in and on the way out, and you can just guess who got it on the way out. So, but anyways, as you're reading through Gibbon's descriptions of what Maximin and his reign and his, I think it was brief. He'll be using pronouns like he and him, and and then they, or So the question is, what are those referring to? They're referring to something further back in the text, right? So to kind of link all those in is a giant task. So with text extraction, what you might wind up doing is first of all, what you do is you're going to scan, and you're going to do part of speech tagging to all the tokens in that whole Gibbon's all of Gibbon. Okay, so part of the speech is going to give you the verbs, nouns, etc., etc. And then very importantly, what also it's going to identify, there's another step there, and that is to identify the named entities, like Maximin, like Julius Caesar, like Augustus, all of Caligula, and then also different provinces, London, Rome, all the cities. So all that is named entities. So you scan for those, because those are actually what are going to be in your tables, right? Right. So this is going to get really hard, isn't it? So then you probably want to figure out some way to kind of extract meaning from that, in terms of predicates, and like maybe you bring in some kind of natural language tool to do that. God only knows, right? So you have all these tools you can kind of bring in. They're all kind of research level quality. God only knows. But one way to do it also, which is the thing more the modern way, is that you're going to specify a set of examples of, like, from this paragraph here, this is the template I want filled in.
And you're going to provide many of those examples, and then you're going to then take all these resources, linguistic resources, and you're going to train them. You're going to do machine learning to get it so that it gets better and better at this extraction task. So the extractors now, I mean, if you really wanted to grab everything out of the decline and fall, that whole text source, it would be, you're not going to get 100%, but you're going to get better and better, and it may be useful to do that. So there's a lot of work going on with this. So I don't think that people are parsing and then analyzing and then putting into a database structured tables like the decline of the Roman Empire. But I think that things like maybe a lot of corporate news, and about it's very fast. Kind of quick analysis or quick pulling in kind of all this data is coming in, all the AP wires coming in, and then you want to know kind of what are the actual actions happening in the world, because then you might want to based on that you might want to like sell something or buy something. So that motivates it from that point of view. But this gives you an idea of like what the kind of universe. I hope this gives you an idea of what kind of text extraction would be all about. So it would be stuff like that. It's a very challenging problem. But very interesting. And just to keep it, I'll bring it up a little bit more, but there's been what is claimed now to be a bit of a breakthrough in the area, and that's BERT. So BERT is this, it's basically it's a way to develop a really, really good language model. So we'll talk about that a little bit. I'm not gonna say much about BERT, but there's a lot going on here now surrounding BERT. So machine learning methods, yeah. So then we have document classification. So this is a little bit better understood. So the idea, this is like sentiment analysis, is a special case. So you usually do this at bulk load time. By the way, this right here, text extraction, you're also doing that you're doing that actually as part of the extraction process. So again, everything's landing in the database in just basic model tables. That's where the results of this are happening. So you have an external program that's going to do all this analysis, and it's going to dump it into the model tables of the database. Document classification, basically you classify the documents that you can usually do this at bulk load time. So you're going to basically go through and you're going to classify them and give them kind of structured attributes, structured values that are going to be associated with them. Sentiment analysis is a special case where it might be like positive, negative, etc. But you could have other things too. You could have other things that you're kind of classifying for. And this is very amenable to machine learning methods, actually. So this stuff has been pretty good. And also, BERT's going to help out here as well. So there's a lot going on there. So this is getting quite good. Sentiment analysis is getting quite good. So what's the sentiment of this particular, I mean, sentiment relative to what, of course, but you could say something like, if we know that like, let's say we have like the press releases of different, or the different, the business wire, right? Is it a positive thing? We have a company, is this a positive statement, or is it a negative statement about that particular company? A report on that company. Okay, then I would say the third one we want to consider here would be question answering. Now, question answering is basically from a giant body of text. You want to go and you want to basically be able to answer natural language questions. So this would be something like saying, all right, who succeeded Maximin? All right, who succeeded Maximin? So who was the emperor that came after Maximin? Now you have all of Gibbon's text of all the decline and fall, and you're going to go through, and there's two variations. The one variation is just to identify the spans or the sentences. All right. Sentences would be like full sentences, and then join them together and make them paragraphs, where this is being addressed. All right, where we're talking about Maximin and we're talking about him on the way out, and then who's going to be coming in. Right, so that's identifying spans, and then the reader can then read into that and then determine who it was. A more sophisticated version of question answering would be that it would actually do the analysis, go in and pluck out the exact emperor who did succeed Maximin. The second one is much more difficult, of course, because you have to do the first one and then the second would be a secondary process on top of that. So those are just a distinction between different forms of question answering. It's not really so clear in our proposed architecture how you would go about doing that. At least how you would ingest the tools they have. I myself work at a much higher level with natural language, and that is over the model database, how you do a natural language. So if it happened to be that you got the information of who succeeded who and maximum, and then another one, and that wound up landing in a table through text extraction. Then a question like who succeeded maximum, going through something like C-phrase, would be able to address that table and pluck it out of there. So maybe you could get this through extraction. But question answering methods and tools are kind of technologies set aside on their own, and how you integrate that into this database architecture that's kind of being proposed here is a bit, it's a bit harder well, it's not immediately obvious how you would. So, okay, so I hope this has been useful, kind of a stream of consciousness presentation of this. Also, yeah, then keep an eye on BERT because it's a big deal. So conclusions for today: semantic web technologies and or some magical way that treat the web as a database are probably largely a pipe dream. Let's be honest. I don't see it happening. Okay, in this private database thing, it's difficult and tedious work to build up a coherent database based on data exchange, extraction, and this bulk load, whatever. But it's doable, and it's presumably valuable. So I think these efforts will continue. I see them getting funded, and I don't mean funded by research. I mean funded by in industry. IR methods are being brought in, unfortunately a little slowly, being brought in to the database to allow SQL-based full text search. And then the developments in NLP really do offer a lot of promise, so there'll be definitely worth keeping an eye on that. Okay. All right, so stay tuned to all that. Okay, so that was my presentation for today. I'll get recitation out by later this afternoon. Yeah, so are there any questions? No, I see a question. There was a question about, is it only sentences starting with Trump? No, we could modify the regex so that it did that. In fact, maybe that'll be something that you'll see in recitation. But no, it'll just grab Trump. Wherever Trump is in the sentence, it'll grab from Trump and then all the way to the end of the sentence. All right. Any more questions? Yeah, and I'll post this up to the YouTube. Okay. All right. Well, I'll see you all next Tuesday then. Okay. All right. Bye. All right. Exit. Stop share. And stop recording.